anything, so I
Okay.
could.
I'll possibly do like a voting. If like 10% of you guys were like 5% or even one people might have a problem with that, I might not do it. But let's see. So like everyone can sort of hear the same stuff. Um, okay. I think it's 2 o'clock now. A little bit of self-introduction. I have been TAing 350 for at least 3 semesters. This is my fourth, so I do have some experience. So I know the materials, like okay, I would say, since I've been TAing this. Um, I'm a ENE student, a graduate student. I'm in my third year PhD. My research interest is in computer vision, not necessarily computer architecture, but I still know the stuff very well. And I know robotics. Yeah, I think that's about me. Just give you a sort of a little bit of self introduction. Also, like, if you guys don't want to stay, like, I think that there's still some people don't feel comfortable being here. Like, you can leave. I'm not taking any participation. Just let you know. And then also, this shall be recorded. I don't know if it is still the same case, holds the same case from last semesters. Usually, this is recorded and will be able to share on the Zoom clouds, but I don't necessarily know. Will that be the same case here? And also, just something that I found out, like if you turn on your camera, you will usually be more focused in class because you know someone might be watching you if you're not studying or following. So if you want to turn on the cameras, please go ahead and turn on the cameras. It will help yourself learn as well. Because when I was taking a class as well, if I close out my cameras, I usually is not studying. I'm doing something else. Usually, like I watch videos, I go to my Facebook, and just see what other people are doing. So turn on the cameras. You'll give yourself a feeling that you're being watched by someone, but usually no one's watching you. But you're being watched. That's like something beneficial just for you guys. Okay, back to the material. This is something I new. I haven't tried. So I have my Surface here. So I try to write it. So I have 2 accounts here. Um, so I think you should be able to see me writing stuff. Let's say, let me draw a block diagram. I'm not very good at drawing though. This is D. This is clock. This is Q. You guys can see it, right? And also, I'm trying to make this more interactive instead of just me talking here, which doesn't really make sense. Like, I don't want this to be like the lectures where like we usually have, like a professor and then a student thing. I'm a student as well. I was in your shoes. Like, I was an undergrad 4 years ago, so we're the same. It would be the best if you guys would like unmute yourself and ask questions, just interrupt me or stuff like that, or ask questions. I would suggest that if you wanted to, please go ahead and do that during um, the time I was talking about, during the recitation, I would say. Okay. So okay, this line, just ignore it. How does it work? It was just random stuff I wrote there. Don't worry about it. So what is MAR? Can anyone answer? What is MAR? So a lot of people have fundamental problem, like understanding of the whole architecture. Can anyone answer?
It's the memory address register.
Yeah, exactly. So it's memory address register. So what does it basically stores values? Store values for address. So register is something you'll hear a lot about this term. Is where like you store stuff, right? Register is some place to store stuff. It's a faster way. It's a faster storage place than memory. So it's faster than that. Okay, so this is storage. But it usually has very limited storage. You only have, I don't know, like 16 bits or however many. That depends on the design. Okay, when let's say for our computer, probably the computer that you're currently using, it's probably going to say 64 somewhere. Okay, what it means usually means that register would be 64 bits. So that's like, you don't see it, but that's how it actually works in the computer that you currently have. So if you are feeding something, let's say while we're doing this Zoom meeting, the commands sent in there will be 64 bits. It's doing all the stuff we talked about. It's doing loading, move, let's say jump, and then write. It's doing all that kind of stuff from behind in the Intel chip, the CPU chip that you currently are using. Okay, that was something about that. So it's memory address. So okay, this MAR stores address. Okay, so that's why it's called MAR. Okay, what about MDR? Was it Joseph who answered that
Yeah, I don't
question?
want to answer again, but it's memory data register.
Okay, I'll try to ask someone else to come in here and answer.
Yeah, I was just waiting for somebody else to comment.
Yeah, so it was memory data register. Okay, so most of the stuff you've seen here is usually registers. It's just a place for you to store stuff. Okay, we can look at some graphs later, but it's just a place for you to store stuff. IR is an instruction. Okay, usually let's say it's in memory, and then you want to pull it into the fetch, decode, and execute cycle. So you pull it from the memory, right? You pull this from the memory. All right, and then you go to so you first fetch. Let's say you fetch, decode into some stuff, and then you execute, and then you get some other stuff. Okay, that's what that's for. Okay, that's IR. So why would you need a block cycle? Why would you the first question for me to ask, why would you need this sort of thing that you learned from 244? Why would you need it? Someone other than Joseph, why would you need it? Someone can answer me.
Yeah, is it because you're kind of updating values so like the MAR and the MDR, and you need to make sure it goes in a particular order, and you use the clock to regulate that order?
Yeah, exactly. Very good point. So the interesting part is, if you think about it, we're electric and computer engineers, so we have both of it. If it's electric, right? If you don't have any block diagram like this, the wires are directly connected, right? So whatever values in the IR will be directly sent to whatever the other end would be. It's just gonna go through, keep going through. There's no way for you to arrange things, and then it's gonna be such a mess that the computer doesn't even know what was going on, right? So you will need something which has like a clock thing. So make sure everything was synchronized. So you will have multiple block like this, which all has the same clock, right? Those should be connected to the same clock. So you will have the same frequency, right? This computer operates whenever there's a change of clock, which means like the frequency goes higher and down. So you usually operates, let's say, from the following edges. So for each following edges, you will get some data from this one, and this one will get a new data from the previous feed, and this one will get a feed from the previous one, right? That's what is it for. Like, so for each one of the clock cycle, you will have things like that. Okay, I think now you have an idea, okay, what this was all about. And then let me talk about, so I think people are asking questions. So, okay, please review anything we need to do to prepare our computers. So I think another thing you would need, basically for the first half of the semester, I think you're going to write some VASP code. VASP means like very simple machine, something like that. It's just a simulator which the professor created in C++, so that it simulates the way you grab an instruction and then you decode and you execute it, right? It's just a simulator. It's basically a simulator. It's not within the same framework. It doesn't exist physically like the computers you're using now, but it's a simulator that simulates the same process. That's what VASP is. And then when you write VASP code, it would be like, let's say 2000 or 000, like, and then you keep writing it, let me put it this way. So it'd be like this. This is the code you will be writing. Okay, it's gonna come out very soon, maybe next homework. You just have to interpret it. Usually, someone will have 2 lines, will be 1 instruction. This is not necessarily correct because I don't know what I'm writing here. Sometimes it would take someone would take 2 lines to say this is 1 instruction. It all depends. So I think we'll come to that later when we go through maybe next week. We will know more. So VASP is like a machine which interpretate these instructions, right? And then so fetch and decode it, which let me know, okay, what this does, and then execute. Okay, that's what this is all about. This is VASP is not used in the real world. This is simply for the purpose of teaching. VASP is for the purpose of teaching. It doesn't exist in the real world. It just lets you know how the system actually works.
So I have a quick question.
Yeah, go ahead.
I think in the in lecture, the professor mentioned how I guess VESP is based off on Neumann architecture. So was the first computer? So it wasn't VESP. It wasn't something like VESP. Was it something like similar to VESP that kind of followed the same architecture?
I think it might be, but I don't necessarily know how the first computer looks like. But I think this is a very good way of organizing it, like the von Neumann's architecture. It gives you like different space of things. Like you have storage, you have memory, you have a controller, and then you have like a data path, and you have other things like that. I think it could be similar, but for other ones, maybe the first computer, I'm just thinking, I don't know necessarily, you can look it up. Maybe you don't have the sort of very complicated thing. You just type in one thing and then you decode. You don't fetch. There might not be memory space when you just design the computer, right? You just, maybe you are using like those kind of old-fashioned stuff. You type in the dots, which dots means zeros and ones. You type in the dots, and then you take that, you feed that little paper into like sort of computer, and then you decode it, and then it may give you another strip of paper, a strip of paper which has 0 and 1s, which means like you did something there. You might not necessarily have memory there, which also could be the first computer. I'm not entirely sure, but I don't know exactly the definition of a computer, but I think that could be the first computer. And also that's how they are doing things when they are running the code. They actually put in the dots in a piece of like strip paper, and then they're feeding that paper into the computer, and then it will get out like another strip of paper, maybe, which tells you, okay, what it does. It does a maybe calculation for that at that time. I think that's that. Von Neumann's architecture is definitely something later, which I think it was 50s or 80s, like when they have like proper definition of a computer. Okay, what's the difference about the machine language from the C++? Okay, C++ is a higher level of language. So when we first started writing languages, these are the languages we write. The 2000, 1000, or 000. These are the ones we write. When you really first started to write languages, these are the ones you're starting to write. And then later on, people come up with more sophisticated languages such as C, right? So it's easy to read and then easy to understand and easy to write. So C is a higher level language than this machine code or machine language. Okay. And then, okay, people are asking how other instructions are executed. So let me just give you one example. So let's say this is IR that's coming in from this end. We have the first clock cycle. Okay, I wouldn't say this is IR. Okay, you're gonna have clock. try to put it up nicely. So when the first clock cycle comes, what you do is you probably would do MAR equal to PC. PC is the point counter, where it usually points at which memory it is. Okay, which memory address it is. Okay, PC equal to PC plus 1. So, and then once you have feeding the current PC, so let's say this is the memory, okay. Let's say the PC will be here before this start. When the first clock cycle comes in, kicks in, this will do, and then this will feed a give in a 1 here since it's change of the cycle, and then you will have this point counter moved from here, so this will be gone, and then we point at PC plus 1. But it's still called PCs, so your PC will be pointing here instead. Okay, so it's like this is a memory where you store all your instructions. Okay, and then you keep feeding it. So with the same clock, the second thing you do, usually you will read. You send the read signal, or you change the read flag. I don't know exactly. Okay, MRD. So you read what's inside of it. Okay. Something else I want to emphasize. If you remember, okay, rewrite this. MAR represents the address. So what does PC represent? It represents the memory or the data, the address or the data. Can someone tell me? Does this PC represents the memory, the data, or the address?
Address.
Yeah, so it represents the address. So when you go from line by line, when you're running the code, right? You go from line by line. So does the DC, the PC, the point counter. It goes from first one to second one to the next one. So that's why PC equals PC plus 1. It keeps going, all right? And then you feed in the address there, and then you want to know what the instruction is all about, right? You don't care about the address. So you do the M here, this function called mem. You read whatever was in the address that's provided. And then return the data. Okay? It's more important for you guys to understand instead of taking notes. That's something else. It's just for me. When I was taking classes, I'm not a cheat sheet guy, so I don't care what notes I have taken in class. I usually try to understand everything the professor talks about in class. I don't really take notes. Instead, I'll borrow my friend's notes to ask, oh, what was going on, if I really want to refer to what was going on. Now you have an advantage that all this should be recorded, or I'll post this online. So you don't really worry about taking notes. You really worry about your understanding here. Once you understand, you're good to go. You capture all this, you don't care about the notes. Why do you care about the notes? Notes is something for you to recapture or trying to catch something that you missed, right? So don't worry about taking notes. Worry about understand stuff here. It's fairly basic concepts. So once you understand, you know, oh, that's not hard. Okay, this class is not hard. Yeah, it's just my way of sort of understanding this whole process, learning process. Okay, and then what you do is you feed in. So now the MDR stores whatever instruction you want to execute, right? So IR will become NDR, right? And then you have another D and Q. I have to erase this. Let me see if I can move this around. So now it's like an execute signal, right? I almost sort of give you what like your homework should be. This is going to be exact same thing, and it's gonna repeat again and again and again. You're gonna see this fetch, decode, and execute. Okay, this is basically fetch for that clocks. You just get it from the memory, all right? What is this? Okay, this is for the previous stuff. And then this is like a go signal. Once everything has done, this is like a go signal. So usually you will have an AND gate ending this signal here from whatever stuff that you want to do. And this is going to be your decoder. I don't know how many instructions you have, so it depends. Let's say you have 4. If you have 4 of it, what would this be? 4 times 16, right? It's going to be 2 to the 4th. So the number of instructions you could have will be 16. Okay? The decoder. But, so it's going to be 14 lines here. Okay, I'm not going to draw every one of it. Each represents a different one. Why was 2 to the 4th? Can anyone explain? Why is 2 to the 4th?
16 equals 2 to the 4th.
Yeah, like you can say that. That's basically correct. So you have, let's say the number, it depends on number of bits that you want the instructions to have. So let's say you have 16 instructions, right? So you're gonna have to have different opcode for this each 16 for each one of the instructions, right? So let's say 000, 0001 to 1111. So each one of the bits will be 2 times 2 times 2 times 2. Basically what you said, like 2 to the 4th, yes. So the number of instructions will be what you have will be the number of bits for the opcode. Two to the power of that. Okay. Now let me ask you a question. Okay, now I have 18 instructions. How many bits would I need? How many bits would I need? This is homework question.
5.
Why 5?
Because 16 wouldn't be enough. You'd need to step up to the next power of 2.
Awesome. So that's exactly the reason. He just explained there. I'll erase this. Whoever captures it, okay? This is exactly homework question. Okay, so this will change. The decoder will change. Let's say to what? This is going to be 5, right? 5 times 32,
32,
right?
yeah.
This is going to be 2 to the 5 because it's going to be 2 to the 5. So you're going to have that. And then each one of this input will be what? Can someone tell me? What would this input be?
The instructions.
Yeah, the instructions of what?
IR0 through IR4.
Exactly. Okay, everyone on the same page? Like I'm not concerned.
I just have a quick question.
Yeah, go ahead.
So opcode should not be confused for like the register address, right? Opcode, it's 2 separate things. You might have like an opcode of, for in this instance 011.
Mhm.
That isn't also basically the address location, right? So it wouldn't be like 0x0111.
Yeah.
That's
So opcode will refer to, let's say the opcode will usually refer to the first few bits for the IR, right? Register refers to the whole thing. This whole thing with, let's say 16 bits will be called register. I call this register. Is where I store stuff. The opcode would dedicate to the ones that you design here. Let's say this is 4, right? 2 to 4, because you have 16 instructions. The opcode will refer to the first 4 bits of that instruction. The first 4. Almost definitely, yeah, the first 4. It depends on how you design it. And the operands usually be determined by the remaining of that, and then where to operate things and stuff like that. Operands, okay.
And another follow-up question. So when you're talking, and I think you mentioned at the beginning of class a little bit. So when you're talking about like an Intel chip and like 64-bit architecture, that would then mean that every instruction is 64 bits.
Yes.
Okay.
So you have, if you remember, like usually we have 32 bits, right? And then it's not enough because we have more stuff we want to do, and then we increase to 64 bits. And then when you're installing 32 bits of software into 64, it might work, but you're gonna do some tweaks and stuff. But when you're installing a 64-bit software into a 32-bit, it's definitely not going to work. Like for sure, it's not going to work. If you know that, like when you're choosing to download softwares, you'll recall that experience. Like, oh, it doesn't work. Why was that? It's because 32 and 64, because you can't load that. You can't load the registers. Okay, and then okay, let me put this away because I need more room here. To be honest, I prefer blackboards. This is so hard. Okay, and then okay, one of the questions was exactly dedicated to how is a load instruction executed. Okay, it's actually not hard, but you have to understand what load does. Can someone explain what load does? Anyone? What does load does?
Does it takes the data at one address and puts it into the data at the other address?
Yeah, like I think those sort of. You're correct. You're correct. So load basically tells, so you're given an address, right? And then you want to put that data in that address to somewhere, right? Now is okay. Let me tell you, it's to the accumulator. It's like a temporary storage thing. You just want to load that, right? That's what it does. So you want to, so you're being given the address. So let's say, okay, for example, here, let's be more concrete here. For example, okay, this sorry. And then let's say 0, 0, 0, 0, 0. Since we have 5 bits here, this tell you this is for the load. Okay, so what we'll do here. So so the decoder does when this number matches the first one. Let's say this is 0. The first one will start with 0. Last one will be 15. Sorry, 32 or 31. And then when the numbers here matches the numbers at the very end, let's say this is 0, 0, 0. So this will be a 1 that comes out from the decoder. That's what the decoder does. Okay. And then you have an AND gate here. It will give you the 1. Only the 1 happens. That's it. When only the instructions matches the LDA, this load instruction will come into play. Okay. This is. Let me say this one more time. Okay. When so first thing you do is fetch, right? And then you decode it, and then you execute it, right? You will only get a 1 here when everything was done from the previous step, so the IR is correctly loaded. All right, and then this will give you a 1 when the next clock cycle comes, and then when you feeding this is IR, right? And you're feeding the all first 5 bits of the instruction, and then you give it to the AND gates. Only both ones happens, you will execute this instruction. Okay, same applies. Let's say if it's 0, 0, 0, 0, 1. Let's say I gave that, I assigned that something else. Let's say store, right? And then only that happens. Store will execute. You also have to end this line with this line with an AND gate, and then you call this store. All right, then you do the stuff. Okay, only when both conditions happens, you execute that instruction. Okay, let's come back to LDA. I think just example. So what does it do? Basically, what it does, it's gonna store this. This is gonna be the address. If this is for the LDA instruction, the first few bit will be the opcode, where we tell you, okay, it's going to be the load. The rest is going to be the address. Okay. So let's give it a go. So you're gonna need this. So load would also require a flag. It's called load flag, or read flag. Sorry. So first, what you would do is from here, once this will go through, okay. And AR will be equal to IR starting from where? Can someone tell me? Based on this information.
5.
Right. To the end, right? Let's say 15 is the end. Okay, we're using a 16-bit. Okay, this is what you would do. This is D, Q. You're gonna also have a clock, which is the same clock.
Wait, if we start, does it like go from 0, 1, 2, 3, 4, and then those are the load, and then the 5 one starts with the address?
Well, what do you mean? I don't quite understand your question.
Where you wrote 5 to 15.
Uh-huh. So it's gonna, yeah, this is 0, 1, 2, 3, 4, 5.
Okay, then shouldn't it be to 31?
4. Wait, sorry. 4, and then you're gonna start to 5 to the end.
So isn't the end 31 though?
I don't know. Like we haven't really talked about this. Like let's say this is 16 bits. Okay, this is if the instruction we have is 16 bits, it will be to 15. Okay, the last one will be 15, right? If it's 32 bits, it's something that you talked about, this will be 31.
So it depends how. So the maximum for this one is 31, and then it may not be all.
Yeah, but it can be different. It depends on when you what the problem says. If the problem says the instruction will be 16 bits, this will be 15. It will be to the last bit. If they can, let's say a new computer comes, the instruction will be 128 bits.
Okay.
What this number would be?
It would start from 6 to.
No, the starting point would be the same. Let's say this is the same. This remain the same.
Okay, then 127.
127, right? It depends on what the problem tells you.
So how do you know the 5 is the same? Because like the professor's example, it was 3.
Yeah, it can be anything. Like I said, it depends on number of instructions you would need.
So the opcode size and the address size are going to vary depending on the number of instructions you have, and then
Yes.
also depending on the size of your architecture. So you could have
Yes.
32-bit architecture, and you
Yeah.
could have 32, operations. So your memory size would vary depending on that.
Yeah.
Okay. I thought that 5 comes from, because right now the decoder is 5 times 32, 5 by 32.
That's because let's say we need that because we need 18 instructions.
I know. I thought that first 5 came from there, like from that 5, because of the decoder.
Yes, yeah. I think this is because let's say we want 18 instructions, so we will have 5 bits for instructions. So this is 532. Okay, I think you're correct. I think that's what you mean.
Yeah. So if it was 3 by
8.
8, then instead of 5, we would have 3 in the load part.
Yeah. So for here, yeah, exactly. So let's say if you have less instructions, you only have the decoder instead is 3 by 8. Let's say the decoder here is 3 by 8. This will change as well, right? Where's it gonna start? It's gonna start with 3, right? You're correct.
Exactly. So when you asked me about 128, I thought that what what the decoder is gonna be if you're gonna have 128.
That doesn't affect the 128 doesn't affect the decoder. It doesn't really care. The 128 was because the design of computer. Let's say I want the design of computer, the register to have 128 bits. That would be stated, it usually would be stated in the problem itself. It tells you, okay, the computer architecture would have register of this size. Let's say 128 or 64 or 32 or 16, anything like that. It will be stated in the problem. It will tell you.
So it's not the length of the square thing you just drew under there?
No. 128 has nothing to do with the decoder.
Okay.
Everybody clear? So still 5 here, because 1, 2, 3, 4, 0, 1, 2, 3, 4 will be used for the instruction, the opcode. Okay, the remaining will be used for the address. Okay, that's usually the case. Okay, and then this 5 number is determined based on the number of instructions that you would need. Okay, you could listen me out. You could use 6 bits, so this will be 6 times 64 decoder, but that 1 bit will be useless. So that's not usually what people don't want to do, because you have 1 bit less for each register and each memory design, which is a lot. Let's say 1 out of, if the whole instruction is 64-bit long, you will lose 1 out of 64 for every register and every memory and every instructions that you do. So it's such a waste. So usually you don't do that. You're gonna use the minimum number of bits for the operation. So that's why in this case we want 18 instructions. You will have 5 bits. It's like an 8. Okay. Let's continue here. Let's not use this large number. Let's still use 31. Okay. All the clock is going to be the same. If you can connect together, it's fine. If not, just tell me it's like say okay. Oh, another interesting thing about this class, he will design the homework, and then I will provide the solution. He will not tell me what is absolutely correct. So I will come up with a solution and I will grade it. So but like since I've been doing it for some time, so I know what the correct solution looks like. I know what's going on. But I'm sort of trying to tell you how to do the homework during the recitation. So yeah. Like also, if you have questions, then you want to ask, please post it in Piazza, and because people might have similar questions. Okay. I want to go through the end of this because this is going to be very helpful when you are doing the homework. Okay, this will be the first one. I'll give you more space. So you've load what's in that address you want to load, the address here. Okay. You're gonna have another COK. This is gonna be the same thing. So what you're gonna do for the next step? Okay, so let me just tell you. You know the address there. You just get this out. You do a mem, right? That's how you look. That's how you read it, right? And then set the read flag. It's fine if even if you don't do it. But the best you would do it whenever you do a load. You do a read. Whenever you do a store, you do a write. That's something about the ALU. We'll talk about it later. Okay. Everybody understands? So you get the address. This is for a load instruction, right? You get an address there from here, from the instruction. Okay, you get an address, and you want to read it using that. MDR equal to MEM. So MDR will be the register that you store the data. Okay. And the next step, you save that information into the accumulator, and then you can use that accumulator to store it anywhere else. Accumulator is usually like you store like temporal data, right? This is the end. Okay, you guys all understand this? This is important. It's very important. for the load instruction, does everyone understand? Gabe?
Yeah, I do. I was gonna ask because I mean, unless I missed something during class, we didn't go over the accumulator. So the accumulator just stores whatever used to be in the register in which we're loading the new information into.
So you can store temporal information.
So what are instances in which that information is then used again?
What do you mean? So you mean accumulator is used again?
Yeah, so if it's temporary information, so I guess it'll eventually go away. When would you
So-
actually need to
Yeah,
access and
so
use
if you think about it, when you are actually doing the load instruction, right? You're loading the memory somewhere to a register, let's say register A, right? That's what you would do. So you would store that AC into register A or somewhere. I don't know, right? You won't just like when you write a code, you can think about it. You won't just say load some address. But what does this go? This goes nowhere, right? Right? You're gonna have say, okay, load equal to, let's say, register B. So you load that value into register B. So then you're gonna put this AC, as you can imagine, you're gonna put this AC into register B, right? You understand what I'm saying? And then you don't care about AC anymore. It can be overwritten by other commands.
So if I understand properly, so when you're looking at a load instruction, like the operand, which I guess is the next part of the instruction, that's the information that you are loading into the new address.
Mhm.
And then whatever information used to be in that address is going to be in the accumulator.
Mhm.
Okay, got it. Thanks.
Okay, and then okay, I want to ask a follow-up question. It's just because I think I haven't talked about it. I don't know if the professor has talked about it in class. Where does this come from? Where does this go? Anyone?
I mean, after you perform an operation, I would imagine it would go to memory to be stored, right? Because you're just doing, because the ALU is just like a binary, it's just binary math. So it performs some computation and then it would have to be stored in memory.
So if you recognize, so like when we are doing the operations, like the stuff you talk about, like say the add and stuff, usually it was between the lines. Which means like this operation MAR happens while this gives a 1. I know what you mean. That's a very good point. So it's good for me to emphasize that. It just tells you, okay, when this changes, when this line changes, it gives a 1, you operate this instructions as well, like this ones, right? Only this changes, it gives a 1. This is the question that I want to ask about this too, is this is about the whole process of the computer. So what essentially I'm talking about is this two line is connected. So it is actually connected. This thing actually goes back here, feed back in. Okay, let me hold for a second, like for you guys to observe this, or to understand it, or to think about it. This line, which means the end of the instruction. So you made a very good point. Who was that, Joseph? You made a very good point that that you might be going to doing something else, but usually, but this is a description for the process, not like the detail where to do that. So like I said, like usually things are doing while this changes to a line to a 1, and then this will happen. Okay. So this means like when this changes to a 1, which means the execution of this instruction is ended. And that's when you're going to start to fetch a new instruction. So that's why this two lines connected, magically connected. And then everything that follows out, let's say whatever you do here in the black box for some operation that I don't know, whatever it is. And then the end of this will also be connected back to there, no matter what you do. This just describes the whole process of the computer, how the computer is running. And then why there's clock cycles. Okay. Think about that. Like, so this two things is connected. Let me erase this, but you need to think about it. And then it would be the best if you can draw in your homework. So that would be very clear for you as well. I think we only have 5 minutes. I think that, and then also, let me see. So in the lecture, there was a question about why the source address in the move instruction has more bits than the destination address. It depends. Like, I don't know how big is the memory. Let's say you have the address here, right? The number of information you can store is, let's say, 32 minus 2 to the 5. 32 minus 5, 2 to the power of that. That's the number of information you can store. But if your memory is not large enough, so you can have less like addresses in your memory. Let's say you only have, this is what, 2 to the 27. It's like 2 to the 7 kilobytes, megabytes. Let's say if your computer doesn't have 2 to the 7 megabytes of memory, you only have 2 to the 5 megabytes of memory. You will only have less memory, as you can imagine. The memory address is going to be smaller than this number, right? That was the other part. People ask, like, why the source address in the move instructions has more bits than the destination address. So I'm just trying to answer that question. It depends. If the memory that you have is less than this number, because the 2 to the 27, you might have like a smaller addresses for the memory, right? That's what you can imagine. I would give you a little sort of understanding of how the homework 1 looks like. Let me stop sharing. So this is how the diagram looks like. So this is for last homework, previous year's homework. So you're gonna have something similar like this, like the ones I've drew. Right? You just do the fetch, and then you decode it, right? This is 4 times 16 decoder because you only have 16 instructions. But in our homework, we have 18, so you know what you're gonna do. You're gonna take more time on that. And then this is each one of the instructions that you're gonna execute, and then the load was here. The load instruction was here, and then everything was actually connected with an OR gate here. So whenever there's one instruction at the end, which means that's the time you start a fetch cycle. A circle, I'm sorry, a fetch circle. Unless you say halt. Okay, just tell the computer to stop. Unless you tell the computer to stop.
I have a question.
Yeah, go ahead.
Well, one, could you just go over the number of clock cycles for the 3x8 decoder for like the 8 instructions? But also like when we go back to like node A, basically, does that add a clock cycle for every instruction except the halt?
Could you say it again? So you said when we are, could you say it again?
So you know how you, after an instruction is basically done with all the other flip-flops, and then it goes back to like node A?
Uh-huh.
Do we add a clock cycle for all the instructions except halt?
No. Because this is connected. This line is connected. Like I said, this line is connected. If it's a line that's connected without a flip-flop, it's going to be the same time running it, right? Like the ones here. The MAR is going to be instantly run. This instruction is going to be instantly run when this changes to a 1. This is instant. When there's a line connected, there's no sort of clock cycle thing. Okay, unless there's this So like I mentioned with a flip-flop, you will have this sort of clock cycle concept because this will only change to a 1 whenever this goes to the edges from the edges false. This edge is false.
So you could almost count the longest path of flip-flops to get your clock cycle number. Is that correct?
Yep.
And a logic unit or device like an AND or an OR gate wouldn't count towards the clock cycle too.
Yeah.
Right.
Because usually we say that's instant as well.
Right.
Okay, I'll share this. I'll post it. I'll make a folder and post it. Oh, before you guys go, I want to mention something real quick. So the past, let me share screen. Something very important. So please utilize this. So you can find it in ENEE350 files, lecture notes by week. That like it was his lecture notes as well. Like it does a fairly good of classification, not classification, clarification for all the stuff that he mentioned. It does a fairly good job. But like to be honest, I learned by going through these notes, these PowerPoint slides. It's well written, easy to understand, and you can see some of the stuff here. It tells you what was going on. You can take a look at that.
Thank you.
I think, and then you can find previous year's midterms. I'll point it to you to which midterms to look at, but like there's a lot of files from past years stuff, and he doesn't delete. You can definitely refer to. So that's gonna also be a very helpful resources. Okay.
Thank you for all the help.
Thank you for the help.
Yep. I think that's it for today. I'm a pretty easygoing guy, so like that's why I suggest people don't use GroupMe, because if you have any question, like post a private post. If you want to say something bad about us, like about the professor or the TA, make a private post and let me know how we can do better. I can possibly talk to the professor as well. I had very bad comments about me, so says like this TA doesn't do shit. I also have fairly good comments about me, says like this TA does everything he can do to help. So I'm fairly easygoing. I don't care about the comments. I only care about helping the students. So please let me know what I can do. If you don't say it out loud, we will never know. Like I will never know like where I did wrong, where I did okay, or where I did good. You can help me improve on the way as well, so you get more help on the way. Okay, I hope everyone get an A in this class. I will grade pretty easily, unless you cheated. That's like the red line I will never cross. Don't cheat, don't copy. If I caught you, I'll report to the student council. We have done it once 2 years ago. Okay, please don't let us do that. It's not going to be end very well for any of us. Other than that, I'm fairly easy grading. Like the average I gave for each one of the homework usually be 90s or 80s.
Yeah, the homework didn't look too bad, but
yeah, it's not. I pretty much go through every one of it, unless except the one that's about memory. We'll talk about it next week. You have 2 weeks to accomplish it. So, all right, guys.
Thank you.
You guys are mostly comfortable. Yeah, most of you are comfortable saying coming to the 2 lectures, right? Coming to the 2 recitations, right?
Yeah.
Except I think Yakita, I don't know. Yakta says that she can only come in the second half, in the first half of the second recitation, right?
But I can still watch the recording later, so.
Okay. No problem. Let's see. I'll probably do a voting in the piazza. So.
Any office hours? Office hours. Office hours.
Office hours. Yeah, I tend to. That's what I tend to do. I tend to use the first half to discuss stuff and the second half to answer questions. So I don't have to sort of go through the same thing again, since like we're all virtually. In the past time, like we have a very small room, which is so compacted, you can't fit 50 people there. But now we have a virtual one, so I'll see if we can work out like that.
Okay, so half hour what? Can you say it again, please? So
the first half, from 1 o'clock, from 2 o'clock to 3 o'clock, you'll be recitation, which I go over things. From the second half, from 3 o'clock to 4 o'clock, which will be office hour, which I tend to answer questions. I'll do a voting, see if everyone agrees. Unless everyone agrees, I don't think I do that. I'll just have to make another time to do office hours.
I see. So you don't have class now. So after your discussion, it will be office hours. It will be your office hours. It means.
Yeah, unless people all agree that I can do that. Otherwise, it's going to be recitations after recitations.
I see. Okay.
Cool.
Thank you.
Thank you.
All right.
So could you send us the flip-flop circuits you made?
No. No.
No?
I can send you what I drew today during recitation, but I cannot send you those.
Can I see it again though?
No.
I don't.
You can see it again. If there's a recording, you can see it again.
Okay.
But
That's
no.
like
It's like homework solution.
Okay, so I wanted to know if the commands are different. So for the question, for the example Professor went over, first it was add, then it was command, then it was.
It's gonna change. He can always change.
You can always change it. So it's not a.
No, he can always change it. He will tell you which one is supposed to be what. He will say 0 should be add, 2 should be jump negative, 3 should be jump, stuff like that. He will change it.
Even in the problem.
Yeah, he will change it in the problem.
Okay.
It's not going to be the same.
Okay, thank you.
Hi, I got in a little late to class. I was stuck in the waiting room. Can you explain what you were planning on doing with recitations? Or
so I was saying, I was hoping everyone agrees that I will use the recitation the first hour from 2 to 3 to be recitations for all 50 people, and the second half will be office hour for all 50 people. So I don't have sort of talking about the same thing again, and then people can be more beneficial, like using that time to answer questions or just go do whatever you want.
okay, yeah, that would be fine with me. But
yeah, but that has to be agreed by everyone, almost everyone, I would say.
Yep. Okay. Thank you.
Yep.
Sorry, I have a question.
Yeah.
Is the discussion at 3 still happening?
Yeah.
Okay, because I didn't see it on the Zoom page, but okay.
I meant it to be the same. I think I created another one.
Oh, okay.
I can make a post on Piazza. Just toss that. Hello, everyone. Can anyone hear me? Just give me like a yes.
Yeah.
Hello, yeah, we can hear you.
Cool, cool, cool.
Yep.
Okay. To give you a brief self-introduction before we started, like I always did. I'm a third-year PhD student from EC department, and then my research interest in computer vision. I do a lot of things related to robotics. I've been TAing for this class for at least 3 semesters, so I know this stuff. Wouldn't say fairly well, but I know this stuff. Yeah, that's it. That's all about me. I have a question for you guys. Because I asked the previous session, I was saying, can we use the first session? So we have 2 sessions, right? One from 2 to 3, one from 3 to 4. Can we use the first session as recitation and the second session as office hours to answer questions? But I know this definitely have to be agreed by everyone, since like if you cannot attend, like which I cannot do that. That's what I try to do. So if you attend the session and if you want to stay in the office hour, that'd be fine. If you don't want to stay in the office hour, you can leave. And then I don't have to teach the same thing twice. I wonder if you guys would want to do that or not.
So like you mean come to the 2 o'clock one, and then we have the option of staying up to 4 o'clock.
Yeah.
Or 3:50. Okay.
Yeah.
Yeah, I should be okay with that.
I think that would be beneficial for everyone, for me as well. So because now I'm just going to go through this exact same thing that we go through last session, right? When we have like in-person classes, like because the room is usually very small, you can only have like 25 people in the room, which is not allowed. Now, because we're doing everything online virtually, so I think we can possibly do that. That would be beneficial for everyone. That's my idea. I'm probably gonna do a voting, like put a Google form or something, like see if people wanted to do that or not. If there's like 20% people says like, yeah, no, I don't want to do that, I'm probably gonna withdraw it. Okay. Just to let you guys know. Okay, I'm just gonna go through very basic stuff for you to understand the class a little bit better. And then along the way, I will go through some concepts that might be important, or even go through like some important information that's related to the homework. I will not going to go through some stuff related to memory, how the memory was loaded and stuff, like make a flip-flop for that. That will be for the next recitation next week. Okay. I can't cover it, but like, can someone answer me what is MAR? I don't know. How should I do this?
Memory address register.
So what was that for? Yeah.
Memory addresses.
So yeah, so MAR is memory address, which usually store the addresses. That's what it stands for. Okay, and then you call it register. Okay, you call it memory, but they are all places for you to store information. Okay, that's the same thing. So it's all for storage purposes. And then also whatever it stores the value of that address. Let's say the address would be 1112, whatever you want to call it, or you can say it's hex value FFFA. So that would be a value, would be where things were pointing at. Okay, and then you store that value. Okay, usually that's place for you to store addresses. Okay, and then we have this concept of MDR. Okay, store the data. Okay, usually it stores the data from the memory. And then when you are calling a function called MEN, right? Let's say you do MDR equal to MEM of MAR. So what do? You load. Let me draw a diagram, which is more clear if I do it that way. Let's say the MAR. So usually this is a point counter, okay, and then you put that value into MAR. Okay, so the MAR stands for, okay, this is the address for this block. Okay, and then whatever data was in there, let's say we call this data, can be anything, can be any number. So we want to access this data here at this particular address, right? Let's say I want to go into your house. I want to know what people were in your house, or are there any animals in your house? That was the data we're looking for. The MAR will store your address for your house. Okay. And then this is what you do. MEM basically access whatever was in the address, right? And usually you store it back in MDR.
So does MEM just dereference the pointer?
You can think of it like that. Yes.
Okay, thank you.
You can think of it like that.
So the memory address, like access register, is kind of what stores the address. I still don't really understand the difference, to be honest.
You sort of understand or you don't understand?
I don't.
You don't understand the difference between MAR and MDR?
Nope.
So, okay, put it easier. It's like you can store the address into the data, but it's confusing. Okay, it's just registers, right? But you give it a name, which means like what you want to do with the register. Okay, you understand what I'm saying? You can't do anything with it. It doesn't matter. But I give it a name so I know what's usually be in there and then how I use that. So that's why I call it MAR and call it MDR. You could like, but you could do, let's say, you could like, let's say MDR equal to PC. You give this address, okay, you put that into MDR, but it's going to be confusing. You're going to be doing mistakes when you are doing the programming, okay? So let's say when you have parameters, when you're doing the program, you want to give it a proper name so you know what that does. So that's why you can name it anything. You can do anything with it, but we choose this name to let it know, okay, I does that. So we typically put address into MAR. We put data into MDR.
Oh, so the addresses go in MAR and the data goes in MDR. What's the difference between address and data?
You want to say something?
Oh, I was just gonna say, it's sort of the same thing, just to make sure. So the MAR grabs the address of, I guess, the instruction that is to be fetched from the memory, right? It's about instructions.
Yeah, it could be, or it can be
or
something else.
Or address for data.
Yeah,
and and the MDR, like the other guy said, it dereferences it, or maybe it's basically the data that MAR is pointing to.
Yeah.
Or has the what's in the address that it holds.
Yeah. Yeah. So I want to say this again. So MAR is the address. Like I said, like you have an address for your house or for where you live in. Okay, but I don't know what's inside of that house or apartment. Okay, so the data represents what's inside of that address. The address just represents where it is that everyone can know, or this computer architecture can know. Okay. Does that answer your question?
Yeah, kind of. Thanks.
So what is IR?
Instruction register.
Exactly, instruction register. So it's where you usually store the instructions in. Okay, you store the value in there. Okay, I know there's an instruction. It's 16 bits. It has some numbers in there. I just store that value into this register. Okay, so where you store it. And then like with this IR, this wouldn't be necessarily correct. So you fetch it from the memory, and you decode it into IR, and then you execute. Okay. So like whenever you was done, you would be done decoding. Okay, I'll call this decoding. I'll call this fetch. When you're done decoding, you will get the instructions in the instruction register. Okay, and then you will do the execution.
So you copy address datas or whatever you want to, you copy the address of the data into MAR. You then quote decode or for some reason store the data in MDR, which you then copy into IR, and then you're ready to execute.
Mm-hmm.
Okay.
Like you see over here, this is exactly what you just mentioned.
Okay.
Just let's do a quick scan for this. Okay, it's MAR equal to PC. Okay, so exactly the address you mentioned, right? You put it into MAR, PC equal to PC plus 1, because then it's ready to go to the next one. Go to the next instruction. Let's say you're porting at here. This represents PC plus 1. Okay, and then when you're done fetching it, the point counter will go to the next one. So you know the next instruction that you want to execute. Okay. Read it just a flag when you are doing when you're doing loading. Okay, read it just a flag. So you execute this MEM. You execute this. Okay, and then MDR will equal to that, which is exactly what you said. Whatever was in that address, I want to access it, right? I put that data into MDR. Okay, and then MDR is not our final destination. Our final destination is instruction register, right? You put that information you obtained to IR.
Okay, so MAR and MDR are essentially just temporary places to store things.
Yeah.
You're cycling through them constantly. But
Yeah.
does IR store a list of instructions, or is it also just only
one?
It
IR
just only holds one. Okay.
Only holds one at a time.
It holds the current instruction, right?
Sorry, could you say it again?
It holds the current instruction.
Yeah, it holds the current instructions. Yeah.
And of course, I guess MDR, it puts it in IR and it frees up MDR in case the instruction has to use up stuff from memory.
But you don't care about what's in MDR anymore. That's once you load it, because that might be overwritten in a later instruction. Like in later, let's say in one example here, this is doing the loading. Okay, the MDR will be overwritten. You don't care what's inside there anymore. Because all these registers are served as temporal, like temporal information.
Also,
they just put it there, and then once it was done with its purposes, you don't care what's in there.
Of course.
So all of this stuff, is this all part of like the fetch instruction or the decode instruction, or what instruction is this? Fetch, decode, or read? Well, fetch, decode.
This is fetch, decode.
So this is all fetch and decode, all those steps that you showed us.
Yeah.
Right.
Why do you put it into MDR first? Wouldn't you save a clock cycle if you just put it right into IR?
That's what you usually do things. You can think of it
it's just how it's done.
Yeah,
Okay.
I would want it to, but like when you're doing MEM, so you by default it goes into MDR first.
Okay.
I know what you mean. Let's say can I just do IR equal to MEN of MAR, right? Just save one step or save one clock cycle. No, I can't do anything about it. No.
It's for simplicity of the architecture, right?
Yeah.
Also, I don't know if you'll be able to answer this because this is very specific to something he said, something professor said specifically in one of the lectures. I remember he was saying, I wasn't quite paying attention very well, but he said something like it saves a clock cycle if you put, man, what was it? It was like you save a clock cycle if you load PC into MAR if you do it a certain way. I don't quite remember. I don't know if you remember what I'm talking about exactly.
I don't know, to be honest. Okay, let's come back then. Okay, since I don't recall when he said that. If you recall, or you can post a question on PSI. I think that's a better way. Okay.
Gotcha.
Yeah, let's come back here. So this is talking about fetch and decode, and then talk about execution, right? I want to answer some questions first. So people ask, please review anything we need to do, prepare our computers. You could possibly do, if you have, I don't know if you have done C++ programming before. If you do, you might have Visual Studio. You're probably gonna need that. If not, you can sort of install a small Linux in your Windows to install like G++, which is a C++ compiler. Use that to compile the VASP for you to get it executable like what he has in class. Okay, that's something you can prepare. So basically, you want to compile a C++ file. In order for you to do that, you're probably going to need a Visual Studio or a Linux machine. Okay, whichever way you prefer. You can have a Linux machine within your Windows, or if you have Ubuntu, that would be the best. That would be even better. Okay. So what is VASP used for? What's its purposes? VASP is just a simulator. It's a machine that he used for teaching purposes. The professor used that as for teaching purposes. It doesn't exist in the real world because it's not physically represented in a computer, but it tells you how a computer works and how the architecture of the computer looks like a voluminous architecture, like how is that looks like. That's what we use for is for teaching. The purpose is just for teaching as well. It just teach you guys to understand what was the computer looks like, how it was executed within the computer. Okay. What's the difference about machine language from C and C++? The machine language is language like this. Okay. Let's say this is VASP. We have VASP instructions, which is machine code, which is that's a 2000 1000 000. This is a machine language. It's a lower level programming language. So the computer can understand.
What are you referring? Sorry, what are you referring
machine
to?
language or VASP language, VASP programming language. You understand what I'm saying? So let's say this is 200, which could represent at like A to B. Let's say, okay, just an example. I'm not entirely sure if that's correct. Let's say 200, which represent this, but when you write it, a machine language will be like this, right? That's what's machine language. And then this is a very low level language that a computer can really easily understand. As for C++, with C, it's a higher level language. When you want to write this, you just write A equal to A plus B. And you assign the values of A, assign the values of B. Right? I think in C, you can just do this. It will probably give you an answer. And you can do printf or stuff like that. That's C. It's a higher level language that's readable, so you know what's going on. But it's going to be comparatively slower than machine language, since like the 0 1s are easy to, you don't need a compiler. You're probably just going to put it in there and then you decode. You can just execute. Okay, that's the difference between this machine language from C or C++. So one is a lower level, one is a higher level. Okay, and then I think one of the following up question was how the loading instruction is executed. So that's what I'm going to talk about next. Let me go through this one more time. It's talking about how you fetch the stuff, right? When the signal comes in, I'll talk about that signal later. When the signal comes in, right, you're always going to have a clock. Why would we need a clock? Can someone answer me? Why would we need a clock? Can't we just connect the wires together and just have a computer run?
We need a clock to keep things in sync. We need, oh man, I think I know this. It's like to keep things in sync. I know we learned this in like 244. It's like for the flip-flops as well. So everything is changes when it's like
Yeah.
rising or whatever.
Okay, let me rephrase whatever you just said. Yeah, go ahead if you want to say anything.
You can't store memory without a clock, right? Like, isn't like for sequential circuits, like by design, don't they need a clock to be able to store memory?
They, I think I remember. They need a clock to avoid like collisions or
Yeah.
like race
So
conditions or something.
yeah, I think that's a better answer. So let's say if we don't have things like this, if you only have one line, the electricity, the speed of electricity is the same speed as light. So when you are feeding something with just wires, everything will be done in the same time, and you don't know what's going on. Like the data, there's no data path. Everything is going to be messy. Like you don't know what's going on, and the answer you get is going to be incorrect. That's why you need a clock. So the only change will happen when this edge goes down. So every time when the edge goes down, only thing that will change, like this will happen only when the this clock edges goes down. Okay. Otherwise, this could all be happening the same time, which we don't know which ones happens first or next. That's something we don't want to see. We don't want the MAR to be the MDR, and then vice versa, right? So that's why we need a clock to keep everything in place, so there's no collision. Like he said, there's no collision between two different instructions. They're executing the different times, so make sure, okay, before I get the values of MAR here from the PC, I'm sure that MAR value is I want it from the PC instead of the previous MAR value, which I don't want it. Okay, that's why you will need a clock. Okay, let's go through this one more time. If you understand this, you understand fetch, decode, and execute. Looks like it's just a diagram, but it actually tells you what was going on. So first you grab whatever was in this PC or this address of this, which this PC stands for. You grab that, right? And then you move this PC down. So this will be PC +1, which means that it moves down. And then you will have the address, right? Second thing you will do, you do a read. This is a flag you will set when you're doing loading, okay? And then there's another flag called write. You would do that when you're doing stored, okay? You're loading from the memory, so this is what you would do. So you send a flag as 1, and then you do MDR equal to mem of MAR. I think we explained this before, so you get the data in the address, okay? This happens, this line means when this clock changes, when this becomes a 1, this instructions happens, okay? At the same time, okay? And then the same thing happens here. This will happen, read will be 1, MDR equal to MAR will only happen when it's changed to a 1, another clock cycle. There is this concept of clock cycle kicking in, okay? The third clock cycle will be, you're gonna do IR equal to MDR. You finally store the values of that into the instruction register. Okay, whatever was in here, let's say this is the instruction, let's say I call it IR1. I essentially get that value, IR1, value of IR1 into the instruction register.
I'm sorry, can you use a different color so that we know where you're talking? I'm sorry, I just fell off.
Different color for what?
For like saying where you are at the moment.
Okay. Let me use
I'm
red.
sorry. I'm
Yeah,
really
that's
sorry.
fine. That's fine. That's fine. Use a thicker one. Okay. So we were here talking. Oh, damn. So we were here. Okay, and then talking about how we load it, and then we talk about IR equal to MDR. Okay, and then you have successfully fetch it, and then you decode. How do you decode? It's pretty messy. you're gonna use a decoder. So let's say, I'll talk about something else first. So when you have 16 instructions, how many bits of opcode you would need if you have 16 instructions?
4?
When you
Wait,
have
how many? 16, you said?
Yeah,
Instruction?
when you have 16 instructions, how many bits would you need for the opcode?
I think 4 bits.
Why was that?
Because 4 bits represents up to 16 values.
Yeah, correct. So when you have 4 bits, so you can have values of 0, 0, 0, 0, 0, 1 until 1, 1, 1, 1, right? And then each one of the bits will have 2 selections, is either a 0 or 1. So it will be 2 to the 4. Okay, so 2 to the 4 equals to 16, so you can have 16 instructions. Okay, everyone understand? So then let me ask you another question. Now you have 18 instructions. How many bits would you need?
5.
Why was that?
Because if you have 4, that only gets up to 16, so you need 1 more bit to get a last few.
Great, great. So let me ask you another question. What about 27? If I have 27 instructions, how many bits would I need?
5 again, right?
Still 5, right? What about 33?
6.
Why was that?
Because 5 bits would only get you up to 32.
Great, exactly. So it depends on the number of instructions, and then you designed what's the length of the opcode. It's based on the number of instructions you're given. So in the homework, we're actually given 18 instructions. So you will know how many bits you would need for the opcode, okay? So 18 instructions, we would need 5, okay? And then, okay, let's suppose we have 32 bits of instructions, and then we need, let me just write it down. We have 32 bits of instructions or register. And then we have 18 instructions, right? And then we're gonna dedicate the first 5 to the opcode, correct? That's what we just talked about. And then the remaining 27 will be the operand. Okay, so the first 5 will be the opcode. The remaining 27 will be the operand. When we were talking in class, he was talking about that's one. It has like 8 instructions. That's why, because it was 8 instructions. So you would need a 3x8 decoder, right? Now, what was the decoder that we needed? Right, this was in class. Now we have 18 instructions. Let's suppose we have 18 instructions, right? So we would need a 5 to 32 decoder instead. Why? Because 2 to the 5. Okay. Some people might ask, oh, why don't we? So with 18 instructions, why don't we give it, let's say, 2 to the 6? So 6 bit to opcode. Why don't we do that? Can we give it 1 extra bit?
It would be like a waste of space.
Exactly, that would be a waste of space. You have 32 bits, that's very limited information, and you wasted 1 bit, which you don't want it, right? So we only give it 5 bits for the opcode. That's exactly the answer I'm looking for. So as of this case, you're gonna need a 5 to 32 decoder because we have 5 bits. All right. We don't need this anymore. And then you guys see it. So the inputs of that will be the first 5 bits of this instruction register. Right? The first 5 will be the opcode. That's why we input that into the decoder. The decoder will only give you a 1 if the corresponding number is represented. Let's say if you were given 000, the first one will be a 0. If you're giving 1111, the last one will be a 1. Only the 31st one will be a 1. Okay, and then for this ones as well, when the clock cycle kicks in, when this one's done, the next clock cycle kicks in, this will change to a 1. Only this, the output of the decoder is a 1, and the output from this fetch cycle is a 1. We execute that. Okay, that's why it's an AND gate here.
Wait, can you repeat that?
When the fetch cycle is done, and then the time comes, okay, when the clock cycle is dropping, this will give you a 1, right? When the fetch cycle is done, okay, and then from this clock cycle, when this ends, when this is ending, you give a 1 here, and when let's suppose LDR is 0000, all zeros, okay, and then you feed in that information. This represents the first bit of IR. This is 0. The second bit of IR, this one is 0. Third bit of IR, this is 0. Fourth bit of IR, this is 0. Fifth bit of IR, this is 0. Okay, that represents that. You're feeding that information. Only that is all met. This decoder will give you a 1, right? You guys must know what decoder does, right? You're given a number and then you're decoding into one stream only when that number is the same as like the number of counts here at the output. Okay. I'll give you another quick example is like they will have many outputs here. You have many outputs here. This is the 31st one. The first one I call this 0. Last one is 31st. You will only have the 31st one's output as a 1. So the rest will be 0, and this will be a 1 unless all these ones inputs are 1. So the opcode will be like 1 1 1 1 1. Yeah, and this will give you a 0. That's the only time, and the rest will be all zeros when this is happening.
So are those let me see here. So the clock and fetch, decode, execute, like the sequence of D flip-flops above the decoder, right? Is that same sequence happening after the AND gate there? The AND gate there.
This just don't look at it here. This is for load instruction, LDA. The rest of this is for LDA.
So that's for the load instruction. After that
when
finishes,
it executes, yeah.
Then it goes back to the top. That's where that O represents it going back over
I was going to ask that question. Okay, you spoiled it. You ruined it.
I'm just trying to
I'm just
I'm just a little confused with how it works because it's very weird.
Just follow my flow. Just follow my flow. I'll go back to that. I'll go back to that. Okay, so only this 2 gives you a 1. You're starting to execute it. The decoding is down here. Okay, so or you can call this cycle decoding. You're decoding IR. You're getting the IR and you decode it. Only this 2 gives you a 1. You're starting to execute this code LDA. Let's say LDA represents 000. Okay. Okay, and then this is what we do. Only this 2 gives a 1. You start executing, so you're starting to execute. What does LDA do? LDA basically reads whatever was that address was given, this address here. So the operand, you're loading that address and tells me, okay, what's inside of that address, right? And you put it in the accumulator. Like we discussed before, all these registers serve as temporal information storage. Like you just store that value of MDR into AC accumulator first. You can think of it as like a temporal parameter that you call it. Okay.
What's IR 5 to 31? What's that?
That's the remainder. Okay. I'll explain this more thoroughly. We're talking about this, right? IR 0, 1, 2, 3, 4, which represent. I'm talking about this. Let me finish, please.
Okay, just.
So that represents the opcode. Okay, the remainder is the operand, and then in the LDA, in the load, it represents the address that you want to load. Okay. It doesn't necessarily has to be 32. It's because we said this is a 32-bit of IR. Okay. What if I change this to 16? This number will change, right? What would this be?
15.
It's going to be 15. Correct. It all depends on the information you provided here. And then what if I change it, the instructions here? What if I say 16 instructions that we wanted? What would this number change?
I don't know.
That this is going to be 4.
Would it be 2 to the 4, I guess? So would there be 4 bits in the opcode?
Yes, this is going to be a 4, and then you're going to have a 4 by 16 decoder here instead.
Oh, so I think the IR 5 to 31 represents like the operands of the instruction, whereas 0, 1, 2, 3, 4 is like the opcode.
Yeah, 0, 1, 2, 3. Yeah, like I said, this is the opcode. The first 5 bits represents the opcode, and then the remainder represents the operand. And then you are basically loading that operand into the MAR. Okay? Operand means like whichever you're operating on operand. And then you're basically loading that information into the MAR and then using a man function we talked about to get the data inside of it.
Is this the decode function? What is it? It's like fetch, decode, execute.
No, this is for loading. This is for loading. This is for LDA function. This is for the LDA function.
Okay, I
so
see.
The parts after there. So after this AND gate gives you a 1, all this start to execute, and this is the LDA function.
Gotcha. That's like the opcode, the LDA, I guess.
Yep.
Right. Okay, I see. Thanks.
Right, and then you also have to have this clock so things doesn't mess up. So you have to have a flip-flop as well. And then when this one kicks in, the same concepts go here. Is when this one kicks in, let's say when the address kicks in, this one gets a 1. You're gonna do the same thing there. MDR equal to MEM of MAR, read it, put read. I think the flag can be either way. I think the flag doesn't really matter for now. Okay, the read is just a flag. Just tells you to read it. And then the next clock cycle, this one you see the MDR goes to IR, but this one MDR goes to accumulator. Basically, accumulator is a temporary storation. You store the information there into the accumulator. That's it for now. So this is for LDA, for the load instruction. That's how it was executed. Okay. Let me erase this. It doesn't matter. And then yeah, I was going to ask this question. So after this was done, right, where does this thread goes? And where does this comes from? Right, this is a question I actually asked from previous sessions. I think someone spoiled it. Okay, I'll just explain here. When the next clock cycle kicks in, when this was executed, right, this is going to be a 1, right? This 1 actually go back to here, which is the beginning of the next fetch cycle, a circle.
Oh, so basically it executes when the next clock cycle comes in or like falls down, right?
Yeah, so basically it gives you information, okay, I'm done with this one. You should start with the next. That's basically what it tells. So it gives you the 1. So this one was actually connected to here.
Yeah. No, I'm just saying, so AC equals MDR actually like what executes when the next clock cycle hits when it goes back, right? When the first
It was simultaneously. It was the same time, I would say.
Oh, okay.
Because like when the line was connected, when there's no flip flops, if there's no clock cycle, the idea of clock cycle is instant.
Yeah.
So that's why I was saying that. So that's why we needed flip flops as well. But like, yeah. So these two are connected. Okay, let's say 31. We have a store instruction, std or whatever. We have a store instruction. So this line will come over here. Okay, this line will come over here. This is connected to the 31. What gate will we have? What will we have? Can someone help me? What gate will we have? Let's say 11111 would be store instruction. This stands for store. So what gate would we have here? Before the whole execution thing. Can someone help? Can someone answer this question?
An AND gate?
Yeah, exactly, the AND gate, right? Only this gives a 1, which means it was done fetching. And only when the opcode matches, I know this is happening, this can start doing, right? So that's why it's the AND gate. Both of these are 1. You can start to execute. And let's say the whole thing here is the store execution. And then this, where would this go? Where would this line go?
Back to the first flip-flop.
Back to the first one, right? But you know, you want to draw it nicely, so you can't just draw 2 lines here. What I would do is let's change it a little bit. So you will have an OR gate. Okay, and then all this should go back to the OR gate. Okay. Make sense? So whenever one instruction is being correctly executed, you get a 1 signal at the very end, and that signal represents the beginning of the next fetch cycle.
It represents the counter.
Well, what do you mean counter?
Or
just the
what's
beginning.
the OR gate for?
Yeah, so OR gate means like only one of this, any one of this. So you have 32 instructions here, right? Any one of this get executed, you get a 1, and any one of this send back a 1, you start the next fetch cycle.
Oh, I see. So it's like a really big OR gate.
Yeah.
Basically.
Yeah. So you essentially you have 32 lines coming in from the end of each one of these instructions. Make sense?
Yeah.
And then your homework is supposed to, okay, I essentially give you one of this. So load, I think load is part of it, and you have jump and other stuff. You fill this in with all this AND gate, and then when everything comes back, there's an OR gate. Okay. Let me briefly show you some graphs. I'm done sharing this. I'll send this to you guys later. So don't worry about it. Okay, this is how it looks like. Okay, all these lines, it's different, right? It all, this is from previous year's homework. All these lines should all go back to this OR gate. Okay, and each one of these represents 1 instructions. Each one of these AND gates represents each one of the instructions, and you have the same fetch cycle here, right? Decode. This is a 4x16 decoder, since there's only 16 instructions. Then for each one of it, it's going to be different. All these lines supposed to be going back to the OR gate, but you can't have a 32-bit OR gate in a circuit lab. So that's what it means. I think that's like, I think I answered all the questions. And then I'm going to share with you something important. So from the ENEE350 files, there's a thing called lecture notes by weeks. Okay, I think this is a very good explanation from what he was talking about in class. I actually learned it from here, from this notes in the PowerPoint slides. It's in Elms files, lecture notes by weeks. Okay, Then it tells you what was going on. I think this is a very good explanation. I think this is for best one, right? There was another question regarding in the lecture. There was a question about the source address in the move instruction that has more bits than the destination address. Can you re-explain? So it could be, let's say the memory is not larger than the number of bits that it can be represent. So the memory is fairly small. Let's say if you have only 16 bits of memory, right? It's fairly small, and you will only need 2 to the 64 bits of memory addresses, and you will only need 2 to the 4, only 4 bits to represent it, right? And then you have, let's say, 12 bits, which you can use as operands, but you don't necessarily need that. So you could have more bits from the source address than the destination address. That's why you could have that. This is fairly important. And then something else I want to talk about is I'm fairly easygoing. If you just don't cheat, don't just copy others' work, I will usually give you like very high scores. If you try it, I usually give you half. Like if you just try it, I'll give you a half. But if you didn't do anything, like it just nonsense to me, like I give you 0. Like I can't say anything to that. But if you try it, even if the answer is wrong, I usually will give you half of the points. I'm very easygoing with the points. And then the homeworks are designed by the professor, but I have to come up with my own solution. So sometimes I might not necessarily be right. I will cross-reference it with you guys. And then if you believe I'm doing something wrong, please let me know. If you believe there's anything I can do to improve, please let me know. I think I'll make a post. I'll make sure that I make a post about the Google form, like the things that we talked about, to make this like a 2-hour session for all 50 people. People can attend the first one for recitation, for the second one for office hours. If you don't want to stay, you can leave. That's what I intend to do. Yeah, that's it for me. Like, if you guys have any questions, let me know.
Yeah, also, sort of coinciding with those slides, the professor showed me pictures from the 350 Spring 2017 folder, and those seem pretty helpful. The
Yeah,
folder.
There's a lot of information. You can also see previous year's midterms. So you have an idea of what's going on. Midterms are going to be very similar. Very, very similar. He's going to change stuff, but it's going to be similar.
So, just to make sure I'm on the right track here. So basically, the machine, it loads PC into MAR, and PC gets incremented by 1, basically at the same time. It loads PC first, and then it gets the actual data into MDR, like the operand, whatever, or the opcode, or basically, you know, the
MEME operation.
It basically gets all of the data.
Yes,
rather.
yes, gets whatever was stored in that address. Yes.
And that gets put into IR, freeing up MDR and MAR, letting them be used in case the instruction uses it. The instruction gets basically decoded, decoder, and then there's execution. It goes back to the same thing with the OR gate. And the PC, and all that stuff repeats basically.
Yes.
And of course, we only have like 2 registers, the MDR, MAR paradigm or whatever, for simplicity.
Yeah, I think you're basically correct.
I noticed that decode, it involves MAR equals MAR plus 1, whereas fetch seems to involve MAR equals PC, MDR equals M, read MR, like read equals 1, IR equals MDR. Well, why does decode only have MAR equals MAR plus 1?
Where was that?
So why does decode, it only has MAR equals MAR plus 1? Like, what is that? Why would it need to read the next instruction?
There's no MAR equal to MAR plus 1. You mean referring to PC equal to PC plus 1?
Well, I'm looking at the slides for week 2. It says IR equals MDR, and then MAR equals MAR plus 1.
I don't know what was that for. It might be a mistake, but like because you don't really necessarily play with MAR.
Okay, but what's so what's the decode step then? If fetch step is MAR equals PC, what's the decode step?
Decode, like the decoder was decoding the opcode, so he sort of knows what was going on.
Oh, but isn't there like a set of code for that? Because like with the fetch step, you have MAR equals PC and MDR equals M.
No, there's nothing like that. The decoder is doing the decoding thing.
Oh, okay. Huh.
Could you share? I think you can share screen. Let me allow you to share screen, so you can let me see where is the MAR equal to MAR plus 1.
Wait, no. Let me try again. You see it now?
Mm-hmm.
Do you see where it says MAR equals MAR plus 1?
I actually don't know. I might ask the professor. I'll come back to you. It's in week 2 PDF, right?
All right, thanks. But bottom line is there's fetch, decode, execute. Fetch involves like MAR equals PC, PC equals PC plus 1, and then all those instructions we talked about in the first slide, I guess. And then decode and then execute depends on the instruction, I guess. Right. All right, thanks. This makes more sense now.
Yep.
Okay.
All right. That's it from today.
Thank you. Bye.
Can I ask a last minute question?
Yeah, go ahead.
So, you know, when we how some instructions have operands and others have source addresses or like a secondary address in like the immediately following bit, like series of like the word, right? How do you decide whether, well, I mean, for some, I guess it's kind of obvious whether you give it an address or like a or like a operand. Is there like a way to decide if you're not sure?
I think it depends on the instruction side of things.
Okay.
Oh, I think I know what was the MAR equal to MAR plus 1 is about. So some instructions would need 2 instructions. So you like so some of, let's say you have 16 bits, so 000, and some instructions, let's say 2000, and then another one following it will be 0001, which this 2 comes up to 1 instruction. You will see that. You will see that in the coming VASP machines, but not in this one. So that's why you will have MAR equal to MAR plus 1, which you will need access to the next one, the next instruction.
To the next instruction if you're decoding the current one.
Yes. Yeah.
No, but I was saying, why would you need access to the next instruction?
Because some of the instructions would include 2 instructions.
Oh, I got you. Thanks.
And like a question that a little branches off of that a little bit is that if your command has a source address or like some kind of address as its second bits instead of an operand, you don't use the IR then, right? Like only IR only if you have an operand.
Yeah, so that's like when you are using MAR equal to MAR plus 1, right? So you're basically telling, okay, this might be the address for the second one, and then this is not instructions anymore, right? Then you might skip it. You do PC equal to PC plus 1, maybe in somewhere in there as well, in the execution phase as well.
So if you were doing something that has a source address, for example, you wouldn't like, you know, there's a line that evaluates like IR 3 through 15 or like some variation of that, depending on the size of your.
Yeah, you might just neglect the first 2 bits.
So would you do that line if you had a source address, or would you only do that line if you had an operand?
I am not sure, to be honest.
Okay, but do you see why I was asking that? Like it depend. Like I was trying to understand, like if we only use the instructional register, in like that's a use of the IR, right? So, and if you have a source address, would you use the IR for that or not? Or if not, would you have to use something else to evaluate the source?
You might use the IR for the address.
You might? Okay.
Yeah, like I was saying, so let's say you have memory add, right?
Right.
You would definitely need another line of your IR to basically tell, okay, what that address of those two memories are. So you might need the second line as indicating its addresses. You will see that when the class goes further in VASP 2.3, you will have an instruction which tells you to read the second instruction as its address and then skip that. It depends on how you design the instructions.
Okay. Okay.
I'm looking at this MAR thing. I think I see what it's doing. So on slide 9, like it shows like for the LDA and the move instructions that it increments it because it's like accessing the addresses there, those instruction addresses for LDA and move, for load and move. And I guess it can do that with MAR because, or maybe it's not incrementing it, maybe I'm reading that wrong, but basically it can increment MAR because MAR doesn't have to be used for like those memory registers. They don't have to be used for the data registers and B. So that's why it can do that for that those instructions. So those instructions don't use the data registers. I think that's how that works, right? So yeah.
Decode doesn't always do MAR plus 1 then? That only applies to instructions where which
You would
use like the
need-
second instruction set?
Yeah, I think so.
Well, I noticed that it says that it shows that in the add step, which I don't think does
I don't know exactly what's going on there, so I had to read through it. So.
Okay then. Well, I guess that's it. Thanks a lot.
All right, I'll post that and I'll post the question. Post the stuff we talked about for the discussion sessions.
Also, I got your message, by the way. The answer is yes. I saw the homework assignment date.
So the due date is correct, right?
Yep.
Okay, cool.
Thank you. Have a good weekend.
All right. Thank you, guys.
All right, thanks. See you.
All right, bye-bye.